Hello, I'm your host, Khari Douglas, and welcome to Catalyzing Computing, the official podcast of the Computing Community Consortium. The Computing Community Consortium, or CCC for short, is a programmatic committee of the Computing Research Association. The mission of the CCC is to catalyze the computing research community and enable the pursuit of innovative, high-impact research. In this episode of the podcast, I interviewed Dr. Behc Achikmeshe. Behc was a technologist and a senior member of the Guidance and Control Analysis Group at the NASA Jet Propulsion Laboratory from 2003 to 2012, where he developed guidance, control, and estimation algorithms for formation-flying spacecraft and distributed network systems, proximity operations around asteroids and comets, and planetary landing. He is currently a professor in aeronautics and astronautics, as well as electrical and computer engineering at the University of Washington. He is also a member of their Autonomous Controls Lab. In this episode, Dr. Achikmeshe discusses his time at the Jet Propulsion Laboratory and what it takes to land a rover on Mars. Enjoy! Here today with Behc Achikmeshe via Zoom. Behc is a professor at the University of Washington. How are you doing today?
I'm doing. Thank you for inviting me, Khari. How about you?
I'm doing pretty well, all things considered. So let's dive into it. Where did you grow up and how did you get involved with engineering and computer science?
I grew up in Turkey. I was born, raised there. I did my primary school education, middle, high school there, and I went to college in Turkey. After college, I had an opportunity for a fellowship to come to the United States to pursue my graduate school career. And I came to Purdue University. During my master's, I studied computational fluid dynamics. Again, my undergrad degree was in engineering, my graduate degrees as well. The area that I did my master's was computational fluid dynamics. Then I did my PhD in control theory. Control theory is quite mathematical area. That's what attracted me to control theory, where I could use advanced mathematics to solve engineering problems. It's an area that's unique in a way that you can apply mathematics on real physical systems. You know, for example, computer science, mostly it's about developing algorithms that you interact with those algorithms via a computer, via your laptop or whatnot, or you interact with them when you go to bank, yes, you interact with the ATM machine, for example. But in control theory, the factor is that the algorithms that you develop interact with physical systems without you being in the loop, if you like. So that's really what attracted me, to have a solid mathematical basis to develop algorithms and to use those algorithms on physical systems, if you like. That was really attractive to me. So that's how I got involved in control theory, I guess.
So I know you spent about 10 years of your career at the NASA Jet Propulsion Laboratory. Can you tell me a little bit about that experience? What is JPL and how did you end up there?
After my PhD was in control theory, but my advisor was a faculty member in aerospace engineering department. So I got my degree from aerospace engineering, my PhD degree. And that's where I was introduced to some of the applications of control theory in aerospace. Then I interviewed with JPL and I got an offer. That was one of the happiest days of my life. I moved to JPL from Purdue University. JPL is a NASA R&D lab, research and development lab, located in Pasadena, California. It is not a usual NASA center like Johnson Space Center. It's called the NFF-RDC, Federally Funded Research and Development Center. It has a different status. But JPL is very well known for robotic exploration of space. Mm-hmm. That's the role of JPL. Its main purpose is to develop spacecraft and the instruments on the spacecraft to go to other planets in the solar systems, Mars and other places. But also it operates spacecraft beyond the solar system. So it does a lot of what I would call robotics part of the mission, robotics missions of NASA. Okay? And the group that I joined at JPL, responsible for developing algorithms, control algorithms, that were used on board spacecraft, both for deep space missions that do not go to planets, but they have other purposes. Like they look at stars, they are telescopes and whatnot, as well as missions that end up on other planets, like typically on Mars. JPL is very well known for those missions. For example, recent one is MSL, Mars Science Lab, in 2012. It has been almost 8 years now, where JPL landed the Rover Curiosity, maybe you remember, in August 5th of 2012. And I had a key role in that mission. That's why I was intimately familiar with that mission. But JPL has plenty of these missions. Before that, it was NER, Mars Exploration Rovers, in 2004, I believe. Yeah. So it's one of the major centers of NASA.
So you worked on a project sending the rover to Mars, you said. So what are the challenges to sending spacecraft to Mars from engineering and computer science perspective?
I mean, there are, of course, multitude of challenges. I'm intimately familiar with a group of challenges, but I probably will ignore some of the others because of my lack of insight in some other parts of the mission. It's a very complicated mission. For example, Mars Science Lab, I am taking that one as an example. It's maybe the mission with most autonomous capability on board to date in terms of planetary landing. That's why it's historical mission, not only because it landed the Curiosity rover, but it's because of engineering reasons. The system was completely new. The hardware was new. A lot of algorithms were new. So, it was in that way a flagship mission, and it's a good example. One of the biggest challenges from a controls perspective is the need for autonomy. You cannot control a mission that will land on Mars in a critical phase of the landing, which is the entry, descent, and landing phase. Mm-hmm. These missions have a long phase before they even get to Mars, right? There's an interplanetary cruise phase where you leave Earth and you try to go to Mars. It takes about 8 months, if I'm not misremembering. Of course, there are things done during that time. We are not just sitting there and waiting. But there are a lot of opportunities to interact with the spacecraft. You send information, you receive back, you may correct some decisions and such. So even though none of these things are trivial, these things are done before, and there is quite a bit of involvement in control of the spacecraft. But once you enter the atmosphere of Mars, and after making the decision to land, okay, we are going in, that takes about 7 minutes or so. That's why they call this phase 7 minutes of terror, informally. There's a very nice video online if you want to watch, made by JPL. So once you enter, you have 7 minutes to land. But sending information back and forth to Mars takes about 24 to 26 minutes, if I'm not misremembering. So it's impossible to interact with the spacecraft during landing. Once you realize that it decided to land, enter the Martian atmosphere, it already landed, basically. You're just getting the information late. Okay? So there's nothing much you can do after that point. Everything is over, pretty much. So this phase has to be done autonomously. And that's a major challenge from controls perspective. You have to make a lot of decisions on board based on sense data. We have onboard sensors that gives information about the state of the spacecraft and where it is, what it is doing, its orientation, many things, its velocity and such. By using this information, we make onboard decisions on how to control our actuators, if you like. We have thrusters. We may have other actuators as well, so that the spacecraft does the right thing to land. And the algorithms that onboard process the sensed information and determine the actions that we have to take on board are designed in the group that I was a part of. And I was one of the key engineers who designed one of the algorithms. There are several algorithms that help land the Curiosity. A set of algorithms were during the entry phase, when you enter the atmosphere and you are trying to slow down by using the atmospheric friction drag. Mm-hmm. And then we open a parachute, we slow down a bit more, and then we remove the parachute at one point because that's not enough either. Martian atmosphere is not very dense. It's like on average 1% of the density of Earth. So now you have to slow down by using your rockets. Like when you see people coming back from space to Earth, you see typically parachutes landing them softly in the water or somewhere in the desert. That doesn't happen on Mars. We don't have that kind of air density to slow us down. We have to use rockets. That's where everything becomes very, very tricky. And you can imagine people spending enormous amount of time to make sure even the rockets will ignite after 8 months in the cold, environment of space. You're entering, suddenly they have to open their eyes up and start the engines. That all these processes have all kind of risks, both from a hardware perspective as well as the software that controls all these processes. You see, so protecting yourself against all kind of faults, and after you do that, protecting yourself against all kind of environmental variations, because you land on a planet, there may be winds, there may be dust storms that may fool your devices, so on. There can be a bunch of things that can go wrong, and protecting yourself against all those things, some of with respect to spacecraft, some with respect to the environment, is a difficult game. We try to anticipate all these factors and develop algorithms that can handle all these variations that you may see and perform well despite all these variations, because we don't know things exactly. And then handling all this uncertainty is a part of controls engineers' job, if you like. That's our major job. Using sensed information such that we can protect the spacecraft's motion by taking the right action so that it safely lands on Mars ultimately. So again, this in terms of software, anticipating all this complexity and writing the software that handles all this complexity is the major challenge. In terms of hardware, you can imagine there are many challenges too. You are going from Earth to space to Mars, all different environments, different temperatures and so on. All these things have a strain on the vehicle. The hardware of the vehicle must handle this. So it's full of challenges. And the other major challenge is more important challenge is that you have one shot, and there's no coming back from that shot. There is no recovery. The first time you test this system in full is when you are executing the mission. There's no other way. So all these factors are really, really making it a high-stakes engineering design. For example, if you design a car, you can test it, you can find issues while testing. That's done routinely. Okay, we do that for a spacecraft of this magnitude too, but you can't test everything. For a car, you can test more or less everything. But here, we just don't have the environment to test it in the right way. When you are entering Mars, the speeds, you cannot replicate those. You cannot replicate the actual conditions. So what we are doing is a lot of well-informed guesses about what will happen, models, if you like. And based on that, you have to put your arms around the problem and make sure that you took all the precautions for the successful execution of the mission. I'm just giving you, I think, a sense of how complex this is,
Yeah.
And it is. When it succeeds, it's a major, major relief and success, in my opinion.
That sounds very difficult. Have there been any major failures of attempts to land rovers on Mars?
Oh, yeah. Other than U.S., nobody succeeded. They attempted, but nobody succeeded.
Wow.
I think more than 50% of missions fail. Mm-hmm. It's almost 50-50. And other nations failed all the time. So they have 100% failure rate, I think, as far as I know. So that means it's a difficult thing to do, engineering-wise. We have been really successful. JPL has been particularly successful with missions starting in the 90s. They have also their misfortunes. That's why it's a very, very risky business. Of course, there's taxpayers' money involved. It's all taxpayer-funded effort. We learn a lot. We gain a lot of capabilities, but there is a lot of risk in that way too. I'm glad that public supports all these activities, and people will work really, really hard to make sure that those sacrifices are met with proper high-quality engineering.
So most of those failures, do they typically occur like in the landing stage, or is it getting to Mars itself, or?
Typically in the last stages, either entry, landing, somewhere there, because that's when, we have sent probes to different planets, asteroids, comets, outer space. Of course, those involve risks too, but It's when you compare, I guess, with entering the atmosphere of Mars and landing on Mars, I think that's an order of magnitude harder. That's why failures typically happen when you are in close proximity of Mars, when you enter the atmosphere, typically. I think it's a level of confidence say that it's typically when you are close to Mars.
Do you know what the speed is on entry of like an object?
I knew that, but let me check. But I think it was over 25,000 kilometers per hour. But
wow.
Let me check. That's a good question. Oh, it says actually, I wasn't necessarily wrong. It's about 17,000 miles per hour.
Wow.
Miles versus kilometers, multiplied by 1.6. Yeah, I wasn't wrong.
That's very fast.
That's very fast. Good news is that the atmosphere is thinner, so that way maybe the heating is not as bad as Earth atmosphere. But the problem is then because of that, you can't slow down enough.
Mm-hmm. So the algorithms that you specifically were working on, what were those kind of focused around?
The algorithm that I worked on was responsible for the flyaway phase of the mission. What happened on Mars Science Lab, MSL mission is the following. As I said, we enter the atmosphere. We slow down with the drag forces. Then we open the parachutes. It's called supersonic parachute because we open it at supersonic speeds. It's still very fast. Then it brings us more or less below supersonic speeds. Maybe I'm lying here. No, it may not. Still, it may be supersonic. But it slows it down even further. Then there's a point at which we cut the chute off and we turn on the engines, the thrusters. They slow us down. And as we come down, this is called the powered descent phase. Powered because we have the thrusters on. And we are about tens of meters above the ground. When we start slowing down, really, we are coming down very gently now. And there's a winch on board, which has literally cables. And this winch lowers the rover down with cables. Okay. And the descent vehicle is hovering over the ground at that stage. And when the rover touchdown is detected, the algorithm that I designed take over, stabilizes the descent vehicle during that time because there is an offloading. Suddenly you are carrying a load of the rover, which is almost the same weight as the NASA's descent vehicle. When it touches the ground, suddenly you don't have that load. So, it's like you drop something and then you will have a transitional effect during that time. And then once that happens, and when we know that the rover is safely on the ground, the cable was cut and the vehicle had to turn and burn at the same time to fly away from the rover and crash as far as possible. That was the responsibility of the controller that I designed. Okay, my job was literally to generate the first man-made crater on Mars. That's pretty accurate description, I would say. So the tricky part of the algorithm was how do you stabilize the vehicle during the contact and then turn it. But when you're turning it, you have to be really careful. If you turn wobbling, you may actually, the thrust plume coming out of the thrusters can cause a lot of trouble for the vehicle. It can affect the sensitive sensors on board the rover and such. So I had to really tightly control this thing and push it as I'm turning it. So when I turn and push it, it's like throwing a javelin or something. You're pushing it as hard as you can. And then I had literally several seconds to push it as hard as I can. And it's done, and then it's on a course to fly as far as possible, basically. And I made it fly around 650 meters from the landing location, which was great because my requirement was about 200 meters. So I beat it with a major margin by using the allocated fuel. That was really successful in that way. And it crashed. And then they took a picture from Mars orbiting satellite. Mm-hmm. You could see the crash, landing side and the crash side. It was a beautiful picture. Maybe I should send you after the podcast.
Yeah, if you send it to me, I'll when I announce the podcast, I'll post a photo somewhere.
Yeah, I actually saw the effect of the algorithm, which was very fulfilling.
Have you been involved with any other projects at JPL outside of landing on Mars?
Oh, yeah. One was, again, a flight mission, not as high profile as Mars Science Lab. It's called SMAP, Soil Moisture Active Passive Mission, which was basically an Earth orbiting satellite with a spinning antenna, like a flat mirror-like antenna. It's like made up of very light material. It is rotating and it's looking at Earth's surface, measuring soil moisture. I'm not very insightful about the scientific objectives. I was again, controls engineer. My job was, there was a RCS system, reaction control system, which is a bunch of these really little thrusters you may see in the movies, any space movie. They fire small plumes. You can see the air coming out of them. What they do is basically by throwing air out, they inject momentum, both translational and angular momentum, to control the motion of the spacecraft, both rotation and translational motion, if you like. My job was to design the control algorithms for this reaction control system, so that to control the vehicle's orientation, if you like, and vehicle speed. So that was my job. I designed those algorithms and delivered them. That's one of the missions. The other is maybe on the more technology development side. These were more engineering missions. These are things that had to be done now. And we also developed new technologies for the future. There were two areas that I was very active. One, and maybe the most important one, is planetary landing, or including Mars landing. And also those techniques inspire some of the techniques being used right now for landing on Earth, like SpaceX landings. People who designed those control algorithms were close collaborators of mine. We worked together at JPL, and then they moved to SpaceX. I moved to academia. There I developed what can be described as optimization-based control algorithms. There's a field of mathematics called optimizational mathematical programming. It has different names. I can explain more later. Basically, these are more sophisticated numerical algorithms to solve difficult decision problems. These decision problems may come from different fields. And basically what I managed to do was, for landing problems, I managed to formulate control problems relevant to planetary landing as optimization problems, which are also not any optimization problems, but numerically tractable optimization problems, particularly real-time tractable optimization problems. And this reformulation allowed us to utilize the existing spacecraft more. What it means is they allowed us to fully utilize their flight envelope. What that means is, let's say I'm landing on a planet. Because of all the uncertainties, I may want to land to a certain point, but I may find myself at a different point. It's pretty much guaranteed that you will not be on top of where you want to land after the entry phase of the mission. So during the powered descent phase, when we have full control with the thrusters, what we can do is we can divert back to the point we want to land. That turned out to be a major flight maneuver. And to be able to compute in real time the maneuver in a feasible manner, in a dynamically feasible manner, in a manner that spacecraft can actually execute it, you need these sophisticated algorithms. And I developed maybe one of the first that was ever tested on a testway rocket. That work started at JPL. Later on, I concluded that work in academia, but that started at JPL. The other technology development project that I was heavily involved in was formation flying. This is when you send multiple spacecraft to space. You may want to use them instead of sending a giant spacecraft, you send a bunch of small ones for scientific observations or other reasons. And how do you coordinate these multiple spacecraft so that they act as one was the control problem. And I also worked in that area quite a bit.
So what are the challenges to coordinating a swarm that's, I guess, different from just a single vehicle?
Of course, by having a swarm, you make the hardware design maybe easier in a way. You don't have to send a big infrastructure around a large spacecraft to space, which is very hard. Payload delivery to space is one of the hardest part of the mission. So you may be solving that problem, but you cause yourself other problems. One is coordination, obviously. Like let's say you send for 5 versus hundreds. You may send hundreds, right? Now SpaceX is sending a bunch of spacecraft. So the main challenge is, from controls perspective, is information passage among spacecraft, getting the right information you need so that you can do your part in the formation, if you like, deciding on what that information is, how do you utilize it so that you do the right thing for the mission. And while you are doing that, you also have to make sure that, your motion, for example, doesn't cause issues. Because now you have a bunch of spacecraft, if you're not careful, they may even collide. Before they were rigidly linked. So the collision wasn't an issue. You were one piece. But now you're going around in space at high speeds, collisions can become detrimental if you're not careful to the mission. So there are both this difficult task of coordinating them. And when I say coordinating, I mean the following. For example, we will have a bunch of mission requirements for a system like this. And this may change from instance to instance. And every time you may have to give some decisions on board autonomously for reconfigurations. That you may have to reconfigure the swan to do one thing, and then you may reconfigure it again to do something else. How do you partition the duties among all these spacecraft is not a trivial problem. Of course, we can have the ground in the loop to make all these decisions, but in some cases, we may not have the bandwidth. We may not have the time. So some of these decisions have to be made on board. Those really make the decision problems very, very hard. And then, of course, as I mentioned, they have their own constraints. Collision avoidance is one of them, for example. And the other difficulty is that since now you make this big system into a bunch of small systems, in a big system, you may have very sophisticated sensors, you may have very sophisticated computing units, things like that. But when you make them smaller, you can put them on board now. You have to live with maybe less sophisticated sensors, less sophisticated computational devices, less sophisticated actuators. Now, how do you do the mission with, with these less capable subsystems, if you like? That becomes a bit of a challenge too.
So, speaking of sensors, how many sensors were typically on, say, a rocket that's going to Mars?
Bunch of accelerometers everywhere, to measure accelerations and such during launch and entry to Mars, because that's when it's important. There are, during the cruising phase, you may have sensors to detect stars so that you can know where your orientation is. We have a deep space network to keep track of the vehicle. Again, those are not my expertise, but, we have those. Those are more external sensors, if you like. During landing, we have a radar. In the next mission, we will also have a camera to do what we call terrain relative navigation. We will take pictures. This is the new big technology. And by taking pictures, we will know where we are relative to the ground, if you like, in the horizontal plane. Typically, with radar, we know our altitude, but we don't know exactly where we are relative to the target in the horizontal plane, or on the plane of the planet surface. So cameras provide that information to us. And since we don't have GPS on Mars, we need something like that. So these are the types of sensors. And depending on missions, sometimes you may have specialized sensors too. They do high accuracy sensing of some quantity, depending on the mission.
So these earlier missions, they didn't use cameras for any of their positioning?
Oh, no. For MSL, for example, we didn't use camera. We only pretty much know the altitude, more or less,
Wow. That's crazy.
That is. But, camera also comes with a lot of caveats. Image processing on board in real time is non-trivial. We are developing a lot of technologies, but they have a lot of blind spots too. So, image processing, though it improved a lot, it's not like, okay, I do some image processing on my laptop and make some errors once in a while, that's fine. You can't say that you're sending the mission a couple of $1 billion. If it makes the error at the wrong time, your mission is over. So this technology is, at least the parts that we use must be really, really well validated, verified and validated. We can't leave things to chance. That's the challenge.
So you say the altitude. So when the rocket is entering Mars, how is the system knowing that it's getting close and it should start deploying these different functions?
During the mission, we keep on estimating the vehicle's position relative to Earth and Mars, of course. I mean, that happens constantly. So, of course, with some errors, when you are about to enter Mars. And, again, when we enter, we really don't know from the ground. It's just after the fact, some delay. But, the vehicle detects it because of when you go from free space to an atmospheric environment, suddenly accelerations that you feel change tremendously.
Right.
Suddenly you have drag forces acting on you, slowing you down. That means acceleration or deceleration in this case. So you detect those things with your sensors and you start taking actions accordingly, And then when we get close, there is a point at which our radar starts working. Not that we know throughout the whole landing, we know this altitude. We start knowing it really pretty accurately after a point. But that is also not like 100% accuracy. At the worst case, we had 100 meters inaccuracy. Think about 100 meters. You may be saying that, I'm 100 meters above, but you already are on the ground. That's a possibility. You see? So there is some uncertainty. To handle it, we had an accordion phase, for example. Mm-hmm. We also incorporate this to our decision making. During that phase, what we did is we let the vehicle go down with a constant tolerable velocity. Tolerable means if I establish contact at that velocity, it won't kill the mission, basically. We are going slow enough. But that means you have to carry enough fuel to allow this slow descent. If uncertainty is large, then you have to cover a larger altitude with this slow descent velocity. That means you need more fuel. So there's always this game of how do we balance fuel need with handling uncertainty and so on. So, though we have some knowledge of what's happening, it's not perfect. And our strategies must handle these imperfections.
Right.
If it makes sense.
Circling back to something you said earlier, because you're talking about SpaceX working on landing rockets on Earth. And I watched a couple of YouTube videos when I was preparing for this where I saw them trying to do the vertical landing of the rockets. So I guess, do you know, what are the challenges to landing a rocket on Earth compared to on Mars?
Oh, yeah. I mean, Earth's atmosphere is much thicker. Mm-hmm. And you're coming with high speeds. When you come from orbital speeds, the hope is that we will have also vehicles returning from Mars, which will have even higher speeds. Now you have to enter to Earth's atmosphere where you are heating up more. There is this heating load, they call it. You have to come down such that, you don't burn the vehicle, you don't cause damage and such. And then you are interacting with a thicker atmosphere, so it's affecting your motion tremendously. And you are trying to aim for a bullseye on the ground, on the water in this case. They have these ships that they land on. Of course, the advantage is you have GPS, for example, your location better and so on. But now you are dealing with a harder dynamical environment with thicker atmosphere. That's the main problem. Mm. And that has been the problem. And that's going to be a problem in the future too. As they increase the payload capacity of these vehicles, they make them larger and such. Landing on precise targets will be always a challenge. Think about also, you're trying to land on something that's moving ultimately, both, in terms of rotations because of the waves and also, because of the currents, So as you're coming down, you have to stick the landing. It's not an easy thing, both from an algorithmic point of view as well as the hardware design. How do you design hardware so that it can take the impacts, forces that can occur during landing? Those are very, very challenging problems. SpaceX has been very successful. But of course, they had their also failures. So increasing consistency, making it almost like taking a flight, that level of accuracy requires more and more development.
Right. So, I mean, I guess overall, what was it like to work at JPL? What was your favorite part of working there, or least favorite part?
I must say the most favorite part is working with people who knew what they were doing. There were a lot of world-class, top-notch experts there. They're sometimes the only expert in a certain area almost. The expert, I mean, not having only the knowledge, but they have exercised that knowledge. They have major amount of experience. Deep knowledge plus experience makes you an expert. And there were people who had these qualities at JPL, technical people. And I loved working with them. And I learned tremendous amount of, not only knowledge, as I said, I learned a lot about their experiences. That was really, really amazing. The second piece is also I gained my own experience. I contributed to missions. I contributed to new technologies. By contributing to missions, I learned how to handle a real-world system. and how to think about it, how to parse the problem so that when you solve each little problem and put them back in, it solves the actual problem. I worked on technology development. Then I learned it's not all about solving a math problem. It's about how to even promote this technology. All these pieces from very technical development to somehow promoting the technology, which sounds like marketing almost. And it is maybe. Learning about all these things was very eye-opening. I mean, that was both technically and in terms of human interactions, I think they were the most fulfilling experiences. And it was almost like a completely new education for me as an engineer and as a researcher. Again, most favorite part is dealing with the experts, top-notch experts, but the least favorite part also comes with dealing with people, right? Whenever you deal with people, you have sometimes good experiences, sometimes bad. It's an organization ultimately with a hierarchy, and within the hierarchy, everybody has to protect certain things. If they don't do that, the institution may be hurt. That's why there are many rules in this environment, and you live in that hierarchy. Sometimes that hierarchy restricts you, and when it restricts you, it's upsetting. But also it enables you, right? That's when you are happy. So when it enables you, you are happy. When it restricts you, you are unhappy. I think you go back and forth between those two, But overall, I think JPL made me the engineer I am, so I'm really grateful that I had that opportunity to work there.
So for listeners who might be interested in working like at JPL or NASA or SpaceX or similar kind of things, do you have any advice about kind of things to expect or, topics you think are more important to study, things you were surprised by when you started working there?
Let me start with technical parts of things. I think, for example, if you want to be an engineer working in controls, let's say, I think it's important to have strong key basic skills, the fundamental skills, Like in everything, you have to have strong fundamental skills. You can't just imitate the outcome of those skills. You see people doing things, right? Like it's true for everything. Like I used to do sports when I was younger, of course. Now I'm doing it just to keep you healthy. And I used to see people doing amazing things. And if you want to just imitate what they do, you will always fail. Because, those skills come with years of working on fundamentals. Sometimes those fundamentals may not look even relevant to what's going on, the output. But, you have to work on your fundamentals. And that's true for engineering and science too. If you don't have strong fundamentals, these fancy moves or results don't come out of something superficial. So I think working on your fundamentals is the key. Rather than being a cool rocket scientist, you should think about being a person who can solve problems. I think rather than striving for being somebody, striving for being able to do things, I think makes you a better engineer, in my opinion. Then you will gain your own character and you will be somebody anyways. Also, when you work in big organization, a part of the job is, again, working with people, which is, unfortunately, we learn on the job most of the time. I mean, even technical things you learn on the job, but you get a lot of training. You get a lot of skills during your education, preparing you for that. But typically when after especially you do grad school, like master's and PhD, you work kind of by yourself most of the time, and advisors, maybe a couple of other students. You are with a limited group of people in a limited context. But when you are in a big organization, you work with a bunch of different people in different contexts. I wish I had learned more about how to work with people with different objectives, with different technical and social backgrounds, because that's when you really get into trouble, right? Because you're not trained for it. You're learning it on the job. You may not have the right sensitivities. And I think that's where our education system is not maybe preparing us as well, We gain experience by interacting with other fellow students and professors, but those are different experiences. I wish there was a bit more formal education on how to work with people. That's the part that I thought that I could have benefited tremendously. How do you do career planning, right? Like, I didn't even think about those things. I went there and I want to just do things. But again, there are other things you have to be cautious about so that, you have a much smoother career and work-life balance and all these things. So maybe if you are conscious of these things in advance, you may prepare yourself better. Maybe that's an advice I would have given to someone else who's coming up. I wish somebody gave me that advice before.
Yeah, I think that's good advice. I think a lot of the, at least U.S. school system, there's not that much teamwork. So then working in a team is a skill people have to learn.
I agree. I mean, that's true everywhere because part of the education system is, I guess, measuring you. Always, they try to measure you. Are you a good student? That's always a question, right? In primary school, your uncle sees you. Oh, are your grades good? They never ask you, do you get along with your friends and do things together? Maybe they ask you, but that's not the primary focus of the questioning. One of the goals of education system is measuring people. Maybe that makes you a bit of an individualistic thinker, which is fine, but I think this collective effort is hugely important. That's how we accomplish things ultimately. And being prepared for that type of effort is, I think, it makes a difference. I wasn't well prepared. I had to learn it on the job.
That's it for this episode of the podcast. We'll be back next week for part 2 of my interview with Behc. In that episode, Dr. Ikmes discusses control theory and the work of the University of Washington Autonomous Controls Lab. Until then, remember to like, subscribe, and rate us 5 stars wherever you get your podcast. Until next time, peace.